Alright, today we're going to be talking about Gaussian elimination. So, Gaussian elimination is another method for solving a system of linear equations with three variables. You want to get your system into what we call triangular form, which looks like this that you see right here. Notice that the first equation has all three variables, x, y, and z. The second only has y and z, and then the third only has z. Each leading coefficients of x, y, and z in this example question are 1, which we'll try to make this happen as best we can, but honestly, sometimes it just can't. This is what we want our equations to look like, because the problem becomes an easy substitution problem, like this example that we see right here. Now let's try a problem together. Here's our problem. So we start out, it says 4x minus y plus z equals 3, x plus 2y plus z equals 0, 3x plus 7y minus 3z equals 6. Now with Gaussian elimination, we have to, and I want to stress the phrase have, to actually start out by eliminating our x. So the first thing I'm going to do is I'm going to combine our rows 1 and 2. Alright, so rows 1 and 2 I'm going to combine by basically doing 4x minus y plus z equals 3, and I'm going to multiply the second row by negative 4, meaning that we get negative 4x minus 8y minus 4z equals 0. At that point, the x's cancel. This becomes negative 9y. This becomes negative 3z. And over here, it still equals 3. Now, while we could leave this as is, I personally would like to make this question a little bit easier. The way I'm going to do that is by simplifying this, since all three of these are multiples of 3. Or more specifically, I'm going to use negative 3, so that we end up getting 3y plus z equals negative 1. So that's going to be our first equation. Now, we have another equation here that we want to make, and so for that I'm going to use 2 and 3. And so that's going to end up being 3x plus 7y minus 3z equals 6. And then I'm going to multiply equation 2 by negative 3. So that becomes negative 3x minus 6y minus 3z equals 0. So at that point, these cancel out. This becomes y minus 6z equals 6. So now we have our two equations. 3y plus z equals negative 1, and y minus 6z equals 6. So all I have to do now is I have to eliminate my y. So I'm going to take my first equation, 3y plus z equals negative 1. I'm going to take my second equation and I'm going to multiply it by negative 3. So this becomes negative 3y, in this case plus 18z equals negative 18. The y's cancel out. Z plus 18z is 19z. And then negative 1 minus 18 is negative 19. That means our z equals negative 1. Now I can begin writing out my systems of equations. I'm going to start by writing equation 2 because it started with a leading coefficient of 1. X plus 2y plus z equals 0. Then I'm going to write the green y equation because it starts with a leading coefficient of 1. Y minus 6z equals 6. And then I'm going to write z equals negative 1. At which point I would just plug these in to the equations. So since I know z is negative 1, if I want to figure out my value for y, I would just go y minus 6 times negative 1 equals 6. That means y plus 6 equals 6, and obviously any number plus 6 that equals 6 means that y is going to equal 0. Now that I know y is 0, I'm going to go back up to our first equation, and I'm going to go in and write x plus 2 times 0 is 0, but then remember, z is going to be negative 1 equals 0. So at that point, x minus 1 is 0. If I add 1, x equals 1, meaning our final answer ends up being 1, 0, negative 1. And that is how we do Gaussian elimination. All right, so let's do another example here. So I'm noticing right now that equation number 1 is kind of already perfect, because if you look, that leading coefficient, in other words, the number next to x would be 1, which is why we're not actually seeing a number. So I'm just going to write that right here, x minus 3y plus z equals 4, because I know that that's going to be my first equation. But now what I'm going to do is I'm going to take that equation, x minus 3y plus z equals 4, and I'm going to subtract the second equation. However, notice all the second equation is currently multiples of 2. So I'm going to simplify this equation by dividing it by negative 2. So 2x becomes minus x. That minus 8y becomes plus 4y. That minus 8x becomes, that plus 8x becomes minus 4z. I apparently can't say the word z. That plus 8z becomes minus 4z, and then negative 2 becomes just the number 1. The x's cancel out. Negative 3 plus 4 just leaves 1y, and z minus 4z becomes minus 3z. 4 plus 1 is 5. Hey, look, we have another great equation to write over here. Y minus 3z equals 5. I'm choosing this equation because it has a nice, simple leading coefficient of 1 once again. Now that I have that, I'm also going to need to combine 1 with number 3. Now I don't have to use 1 and 3, but it just seems to me like it kind of makes sense. So, first thing I'm going to do is I'm going to write number 3, but I'm going to divide everything by the number 3, because 6, 3, 15, and 9 are all multiples of 3. So I'm now going to write negative 2x plus y minus 5z equals 3. Then I'm going to write a second equation, and that equation will be based off of the first one. But instead of using equation 1 as is, I have to multiply it by 2. So x becomes 2x, minus 3y becomes minus 6y, that plus z becomes plus 2z, and then 4 becomes 8, at which point those cancel out. Y minus 6y is negative 5y. Negative 5z plus 2z becomes minus 3z equals, in this case, 11. So we have two equations here. Y minus 3z equals 5, and negative 5y minus 3z equals 11. Now, if we weren't using Gaussian, we would probably want to cancel out the z's. But because we're using Gaussian, we actually have to combine. So I'm going to combine these terms by multiplying the red equation by 5, at which point 5 times y becomes 5y. See, now the y's will cancel out. This becomes minus 15z, and then 5 times 5 is 25. So the y's cancel out. This becomes minus 18z, or negative 18z, equals 11 plus 25 is 36. If I divide 36 by negative 18, I find out that z equals, in this case, negative 2. And there we have our last part, z equals negative 2. So at that point, I'm going to just plug these into the other equations. y minus 3 times negative 2 becomes y plus 6 equals 5, which means if I subtract 6, y equals negative 1. And then at that point, I just plug both of those in. X plus 3 minus 2 equals 4. That becomes x plus 1 equals 4, which means x equals 3. So our final answer becomes 3, and that kind of looks a little weird. 3, negative 1, negative 2 ends up being our final answer. Okay, so let's solve this next equation by looking at it. It starts out with 2x plus y minus z equals 5, 3x minus y plus 2z equals negative 1, and x minus y minus z equals 0. So first off, I'm going to put equation number 3 over here to the right as x minus y minus z equals 0 because our leading coefficient is 1. Now I'm going to use that third equation to both solve with the first and with the second equation. So our first equation was 2x plus y minus z equals 5. And I'm going to multiply the third equation by negative 2 to get negative 2x plus 2y plus 2z equals 0. So those cancel out. Y plus 2y becomes 3y. Negative z plus 2z becomes plus z equals 5. Now let's try this again, but now we're going to use the second equation with the third equation. So 3x minus y plus 2z equals negative 1. And then on the bottom I'm multiplying by negative 3, so negative 3x plus 3y plus 3z equals 0. So these cancel out. Negative y plus 3y is 2y, and then 2z plus 3z becomes plus 5z equals, in this case, negative 1. All right. So as you can see, neither of these two equations are going to actually give me a leading coefficient of 0. So I'm actually going to end up placing 2y plus 5z equals negative 1. But we really could have placed either of those equations at that point. Now, we have to solve using both of these. So I'm going to take my first equation, the red one, and I'm going to multiply it by 2. So 6y plus 2z equals, in this case, 10. And I'm going to multiply the bottom equation by 2 by 3, and that's going to become by negative 3, so that's negative 6y minus 15z equals, in this case, 3. These cancel out. Negative 13z equals 13, which tells me that z equals negative 1. Now that I have those, I plug those into my equation. 2y, in this case, 5 times negative 1, it would be minus 5 equals negative 1. That means 2y, when I add the 5, ends up equaling 4. So y is 2. Now I'd plug those in. X minus 2 plus 1 equals 0, at which point that means x minus 1 equals 0, or x equals 1, meaning our final answer ends up becoming 1, 2, negative 1.